So in this file, I have the one that was labeled Paul test, which I'm assuming is on a regular demo motor. So the first thing I would go ahead and look at is, me personally, I like to look at the time waveform first. So you just click over to the time waveform, and then I like to have the scales be the same. So in this case, this one's already a nice big for me, so I can auto scale it and auto scale it. And then I'd like the same thing down here. So if I press this top button, it'll scale it to whatever this current zoom is in settings. So on the drive side, I don't really see anything out of the ordinary here. I mean, the vibration's a little bit big, but it's not anything to be alarmed from. So then if I want to look at the driven end, I can click this button right here. I'm going to switch to driven. And the first thing I notice is that it's already off the screen, so the vibration's a lot bigger. So if I auto scale this guy, now I want this one to be the same as this, so I can hit top again and it'll resume it. So you can see that the driven end vibration is significantly larger than the drive end right off the bat, and the driven inboard horizontal seems to be quite large, and the driven outboard axial seems to be quite large. And if I wanted to see any of these individual plots, we can turn on and off one of the plots over here, however we choose. Same thing down here. This panel here is completely separate from this one, so any change you do up here doesn't necessarily affect this one. But if you want it to, you can hit the top button and it'll, match them, or the bottom will match the bottom one. So here, if I go back to the drive, again, I don't see anything super unusual in the time waveform, so I'll start taking a look at the FFT now. The FFT starts off in velocity, which makes sense. Most people use velocity. Usually the first step I'll do is I'll set my F min somewhere around 5 hertz or so, or 300 RPM, whether you use hertz or RPM. Usually doesn't mean anything major. I just like hertz. I'm a little bit more used to it, but you could switch that right here if you wanted. So the first thing that you want to do, and this is true of any waveform you take, is zoom in and find wherever your 1 times running speed is, and either type in over here in the phase cursor what your running speed is, like that, or take the yellow cursor and drag it, and you want to get it as close to the peak as possible. And then when it pops up with, do you want to recalculate phase, go ahead and hit yes, and what that'll do is it'll recalculate all the phase diagrams at this given speed, because the phase is per speed basis, so you could theoretically figure out the phase at any other frequency you wanted, but the most common one is your fundamental speed. So now I know that these phase diagrams are going to be whatever the phase is at the running speed of the machine. And the first thing I'll notice is that on this drive outboard, the vertical and horizontal seem to be pretty close to 90 degrees, which tends to point towards imbalance type characteristics. Same thing here on the inboard end. Got roughly 90 degrees between vertical and horizontal. If we go and look at the driven end, the driven outboard seems to show more of a 180 degree difference, which is pointing more towards misalignment. And same thing here on the inboard end, we get closer to 180 between vertical and horizontal. So that would be pointing towards the idea that there seems to be a misalignment more on the driven end as the dominating feature, and more of an imbalance characteristic on the drive. But if we go ahead and zoom in here on these vibrations, if we look at the 1 times, and I'm going to go ahead and hit top so that it'll zoom it. So on the drive outboard, we notice the vertical is larger than the horizontal. Same with on the inboard, and the driven inboard and driven outboard. Across every waveform, vertical is always larger than horizontal. And usually if the machine was imbalanced, the horizontal would be slightly larger than the vertical, because the horizontal axis tends to be less stiff than the vertical axis, so the horizontal vibration tends to be larger if it's in imbalance, because it's the same weight going around, but it has more flexibility in the horizontal direction. But we don't see that here, so this right here would be pointing more towards a misalignment characteristic. But but we can further confirm that with the suggestions. So if we click the suggestions button, we can, usually it would start in phase, but we can click over to the summary and we'll see, oh, yep, it really thinks it's misalignment. And then if we wanted to, we could go through the phase relationships here with the balloon diagrams and see the phase relationships across each channel in certain positions along the units. If we had more units in this train, we could click through them here and see the other ones, but in this case we only have 2, so 1 and 2. But I'm going to go ahead and go back to the analysis. If we zoom out with this auto scale button, we can see the waveform, and the first thing I would do is take this little blue cursor, which is responsible for all these little harmonic guys. So if I click this button, it'll show harmonics. So I'm going to take this blue guy and move it here, but if I'm not really, sometimes on a tablet it's hard to move this, so we have this little thing here where you can click this, and for whatever cursor you have here, so this basically decides which cursor the amplitude gets read. It's like the selected cursor, its channel. So for instance, if we zoom in on this peak using this zoom button right here, and I move this cursor over here, you can see the little square crosshair goes to the top of the peak, and the frequency it's reading is right here, and the amplitude it's reading right here, and this amplitude corresponds to the vertical channel. If I switch this to horizontal, it'll be reading the amplitude of the horizontal one, and then same for axial. But if we go back, this thing will jump the cursor to a peak based on which peaks in the current zoom for vertical are larger than 10%. So this will change depending on which cursor you have chosen over here. But in this case, I just want this 28.835 because I know that's my fundamental. So I just click it and it'll jump that there. And then I can turn on the harmonics, and we can see right off the bat that if we go ahead and zoom in down here, that all of these peaks right here seem to be harmonics. So that's the first thing that I would notice. So there could potentially be some looseness here. The other thing I would say is that because this is a relatively large 120 hertz frequency, this is probably related to a line frequency fault. Demo motors tend to have pretty high electrical noise fault characteristics, so that's probably the cause of this guy. But other than that, this vibration doesn't seem too bad. Then we'll go ahead and go to the outboard side. And again, same thing, it doesn't really seem too bad. The 120 got a little bit higher, so there might be a potential line frequency fault in the motor. Those little demo motors tend to have that. I'll go ahead and scale it to the top, and so that we can look at the driven end compared to the drive. And the first thing we'll notice is the driven end seems to have much larger vibration and more noisier than the drive end, especially when we go between these two. And even if we look between these two, the outboard on the drive, or driven, excuse me, seems to be much larger vibration compared to its inboard end. The driven end, if we go back to the time waveform, seems to have really large vibration. I mean, by comparison, this one is maybe 1 G peak to peak, whereas this is on the order of 12 Gs peak to peak. So this is a lot more severe of a problem than what's happening on the drive end. Another thing that I would notice is that on this driven outboard side, there's this peak right here. And let's say I want to know what that is. So I can look here and see if it's any one of these. The reason it didn't show up is because the axial is the big one. So if we switch this to axial, and now we look at it, it'll show all of the peaks in descending order of amplitude. And here it is, 458. So if we click on that, we can see, oh, there it is. And then we can move it a little bit just using these arrows to get it exactly on the peak. So that looks like it's at the top. And that frequency is 458. So now I want to know, is this in any way related to a harmonic? So one way we could do this is we could bring this guy back over here and hit the harmonic button. But another way we can do it is we can press this orders button, and this orders button will rescale the graph according to whatever the phase cursor is set to. So when we click that, we can see it's close to 15 orders. It looks like it's at 15.4 just about, but it's not exactly 15. So this could potentially be some sort of some large frequency of some kind. There might be a resonant going on here. That would be the first thing I might look at. Another thing we can do is we can turn on demodulation. So this is kind of a feature used to see if there's any bearing faults. If we press this button, we're looking for any peaks in here that basically were not there to begin with but magically show up, because that would indicate that there's a potential bearing fault. And more importantly, if there is a frequency that shows up, if it matches one of the bearing order numbers, it's probably a bearing fault. So here again, we can go and have it jump to that frequency. Let's see here. And we can have it jump to, let's see here. Oh, not quite. But we can move this guy, and that is at 60 hertz, so that's a order of the 30 hertz running speed, so that doesn't seem to have a bearing problem in this location. If we go to the inboard side, again, there's not really any peaks that seem to jump out or magically show up that weren't there to begin with in the original waveform. Same with on the drive end, for sure. Those completely go away. So there's not likely a bearing problem. There seems to be, if we go, let me see here. I'm looking at my notes, sorry. If we switch this scale to acceleration, we can look at the higher frequencies, because as you change the integration type, you're effectively accentuating certain frequencies, and the higher up the frequencies get, the more they can be seen in acceleration. So you notice that when we have it in velocity, we can't really see anything up here that's noticeable. When we switch it to acceleration, they all show up. The first thing I would notice is that there seems to be a lot of frequency vibration up here that isn't really present on any other location, other than the drive or the driven inboard and outboard. So the two drivens are the only ones that have this high frequency information, which is probably the cause of why the time waveform is much larger on the driven side than the drive side. But none of these frequencies show any demodulation characteristics, so it's not likely a bearing problem. The one thing I would mention though is that you can turn on the sidebands and try and see if any of these frequencies are related, because when we go to orders, they don't seem to fall on any orders. And the one that I did notice that was a little interesting was if we try and match this middle sideband cursor to this guy and then sweep this around, or maybe it was this one, we can kind of get it to show that there seems to be, yeah, right here. Let's see here. So if we zoom in on this, I'm sorry, I'm reading off my notes. I looked at this file a little bit earlier, but you can see that this peak right here doesn't fall on an order, but seems to have roughly 30 hertz sidebands, probably almost exactly 30 hertz. If we zoom in a little bit even closer, I might be able to tell more, but you can see that if I really put this guy on this peak, then it basically lines up with all these other peaks. So that might be some sort of fault, because we have a frequency that wasn't in order to begin with, but has its own sidebands that seem to be at the fundamental order, which can sometimes happen in some bearing defects. The last thing I will show is if we go to the animation, which is this APA button, we can see a rough animation of what the shafts are doing at our one-time speed. So normally you would start out here, then we can click from single view, go to we can switch to a single view, which only shows us one direction, which is the one I personally like. Then we can choose to amplify it or de-amplify it, depending on how big the vibration actually is, or zoom in and out. And then we can change the viewing angle. And the one I personally like is the axial one, because I can kind of see a little bit more. So here it looks like the blue shaft is very, across itself it's very in phase, so it's all moving in one direction, which tends to point towards a type of imbalance characteristic. And that's probably also likely because the orbit seems to be very relatively circular, which is pretty characteristic of imbalance. But the red one, you can kind of see it that the outboard of the shaft, if we go to the horizontal, is moving a little bit lagged behind the inboard, and more importantly, when we go back here, it seems to be very flat responses, and the flatter the lines get, the flatter the orbits get, the more likely it is to be misaligned. Whereas the more circular it becomes, the more imbalanced it is. An old saying is that what goes around comes around is the characteristic of imbalance, because you can imagine a weight going around, so it should have roughly the same measured vibration all the way around. So this kind of confirms what we saw earlier, that the drive end, the blue one in this case, seems to have more of an imbalance characteristic from its phase relationships, whereas the red one seems to have more of a misalignment characteristic from its phase relationships. And this just goes to show that most machines don't really have a clear run-of-the-mill, like 100% imbalance or 100% misalignment. Usually it's kind of a mix between these two. So in this case, the blue one is probably a little bit more imbalanced versus the red one is probably a little bit more misaligned. But the other thing to keep in mind is that really in this vibration, the thing that really seems to be of potential concern is that all the vibration we see here really high up on the driven end. And so the first thing I would probably do after this is to go and try and run a resonance test or a bump test or something to see if any of these frequencies are resonant, especially this guy. This vibration here at like let's see what it is, 454, seems to be really resonant. It's unusually high, so there's probably a resonant going on right there. And from the looks of it, if we zoom in, it seems to only really be affecting the axial and the vertical. So chances are there's a resonant that's slightly off angle between the axial and the vertical. So that might be something to look at. The last thing I'll mention is up here in the report, you can press this report button and then go ahead and name this something. So I might just call it Paul Data Set on demo. And then if I hit this report pics button, it'll automatically create a bunch of pictures for me that kind of summarize what it found and what sort of data is here. So if I click this, it'll run through some things, and then it'll ask me, it'll pop up with, here's the drive unit, and then it wants me to, based on my, understanding of what I think is going on, kind of decide whether I think it needs to have repair on like a 1 to 5 scale, with 1 being needs repair and 5 being perfect. Where do I think it is? So in my case, I think the drive end is probably okay. I think it's probably at about a 4. It seems to be largely imbalance dominated. Other than that, not too much of concern, right? And then we hit accept, and then it'll pop up with the driven. And the driven one, I think that one is a little bit less. I'd say maybe a 2. So it pops up with what my previous comment was, in case I have several units and some of them are the same. So this one, I say it seems to be more dominated by misalignment characteristics. It has large vibration amplitudes of almost, if I could spell, almost 12 Gs peak to peak, and has large frequencies with high amplitudes. Also a very large peak on the driven outboard at 458.5 hertz, likely caused by a resonant between the axial and vertical. Would recommend performing a resonant bump test as next action. So then after I'm done putting my comment, I can hit accept once it's done with all the units, and then it saves all of those as basically pictures. So if we go computer, C drive, we go to where all of the files from the DT6 are, Update International under C. And then in this case, instead of going Smart Sensor Data, which is where the files get saved, we're going to go to Reports. And here's the one it just saved, Paul Data Set on Demo. So if I open that, here's a bunch of pre-formatted pictures. So you can see here's like on a unit level, roughly what was happening. So here's the 1 times vibrations, here's the phase plots, here's the orbit plots, here's my comments. Same thing with the driven. And then down here, these are probably the interesting ones. These are basic summaries of all the vibration. So this, in this case, is the drive on the front left side. I tried to stick away from inboard and outboard just because it is a little bit confusing sometimes when you get to multiple unit machines where there isn't really an inboard or an outboard on the middle unit. So front left becomes a little bit more easy to understand once you decide which side is the front side when you take data. But so here, this one just shows you all the vibration in orders at whatever running speed I chose for the front left on the drive side, and then it lists out all the harmonics of significant amplitude and what their measured vibration is. Then we can click to the next one, and it'll be the same drive front left side, but this one is a combination between the waveform, all of the crest factor, peak to peak, RMS, kurtosis values, and then a basic FFT that lists off the largest peaks in order. So here we can see right off the bat there's a relatively large peak at 4.022. Like I said, this is probably that 120 line frequency, because that's right. This 4.022 is exactly at 120, so it's probably some sort of line fault. Then the next one is a zoomed FFT versus an FFT, so it zooms in on the lower orders and then zooms out for the higher orders, so you can see what's going on down low, because that usually matters a little bit more, and then you can kind of get a full picture. And again, it shows the largest peaks in each category. And then here's just, drive front right, so it's the same information as the previous, but on a different position. And so basically for every position, when you take data, this will automatically make 3 table charts for each of the positions. So since we took data on 4 positions, with each giving us 3 charts, we're going to get 12 pictures in this case, plus a picture for each unit. So we could use that in a report or something. We're working on getting these to output to a PDF at the moment, but at the moment it's not quite done yet. But like this one, for instance, is a little bit interesting. This was the driven on the front right side, which from our original picture, driven front side right, so it's this side. So in this case, it's the outboard. You can see the crest factor colors are starting to light up. They're a little bit less green. As the values get more and more indicative of faults, they will go more and more towards red. So it'll kind of go through green to yellow to orange to red. And so right here you can kind of see that these crest factors on the vertical and horizontal of the driven on this outboard side are starting to show some sort of high vibration potential issue. So it can be useful if you don't really know a huge amount about vibration. You just kind of want to get an idea of whether or not it's worth it to call someone. You can basically just take the data and then hit that report and hit make picks, and you'll get all these, and then just based on the colors you can get a rough idea of whether or not it's worth having someone look at. I think that's all I have for this vibration. One thing I will mention is you can go ahead and hit this sound FFT button on any plot, or you can hit this play sound button, and what that'll do is there are 2 different ways of listening to the data so that you can actually hear if there's anything unusual about it. I won't click it now because it doesn't tend to work super well over a Camtasia. It can't really give you the sound that I can hear on my end, but if you want, you can press that button and you can actually hear your data and then watch an FFT as it moves along to see if there's any noticeable trends in it. When I did it on these files, it didn't show anything out of the ordinary, so it wasn't really, but there have been other times in the past where I've managed to be able to like hear when a certain arm was moving for a spindle blade, and I could hear that the piece was resonating the moment the original impact happened. You could hear it ringing afterwards, and that's where most of the vibration came from. So it can sometimes be useful. But other than that, I think that's mostly it for this file. It seems to be that there's potentially something a little bit awry on the driven end. Maybe not concerning at the moment, but that one peak right here that's really high at 458. That's kind of a concern, and I would probably run a resonance test next, which you can do with other parts of the software, whether it be a bump test or actually going through the entire effort to do a 10-point plot, which is arguably the best. It just takes a long time and is a little hard to get used to doing, but it'll tell you if you have a resonant and then where you should put your stiffening supports or your weights to try and get rid of it. But I think I should do it, and I hope this helps. If you have any questions, feel free to email me or call us. We'd love to be able to help. And I hope that you can get a little bit out of this. I'm sorry it was a little bit long. I tried to cut it down a bit, but I figured I'd be a little bit more thorough than I usually am. Just to try and give you an idea of all the things you can do with the software. You can also like make circle plots, which I did. It didn't really show anything interesting on this, so I won't really go through all that. But there are plenty of things in here that will let you analyze whatever you have that comes in, and I hope that you can find some use in it. Thanks, and I hope you have a good day.